Welcome back to section 3 of chapter 0. In this section, we are going to be looking at exponential functions. Now, exponential functions can get a little bit tougher than what we're going to look at now because we're not really going to be solving exponential equations or anything, because doing so requires logarithms, which we're not going to get to until section 5. So we'll be able to do that at that point. So right now we're just going to be looking at the graphs. We'll be solving by looking at graphs, look at the rules of exponents, and some basic stuff. So our learning targets for today, we're going to be able to graph exponential functions and state their domains and ranges. We're going to be able to rewrite exponential functions by changing its base. Find zeros of exponential functions. Solve applications involving exponential functions. And find an exponential function using points in its graph. So, and some of those will go beyond what we're actually going to look at right at this very moment. Exponential growth and decay, exponential functions, have the basic form f of x equals a to the x. Some number to the x. A is called the base, and it must be positive, and a can't equal 1. Because if a equals 1, we have 1 to the x, which is just 1, which is a horizontal line. It's not an exponential function. So it has to be positive and not equal to 1. And then x is called the exponent. So here, notice the variable is in the exponent, which is why it's called an exponential function. So the graphs of exponential functions, if we look at the graph, we're going to, let's let b equal, or a equal 2. So the graph of f of x equals 2 to the x. And it doesn't have to be 2. It could be any number we want, as long as it's bigger than 1. I'll tell you why in a second. When we graph this, it's going to have a horizontal asymptote of the x-axis as it's going to negative infinity. And then it's going to curve up, and it increases very, very quickly. An exponential function is the fastest increasing function. So that's what f of x equals 2 to the x looks like. It has this horizontal asymptote going this way, and then it increases. If we had f of x equals 2 to the negative x, that's going to be a horizontal reflection, and could also be written, since that negative, that could be 2 to the negative 1, which is 1/2 to the x. Those are the same thing. That horizontal reflection makes the asymptote go to the positive infinity side. So generally speaking, this first one is called growth, and the second one is called decay. We can also flip them upside down. If we made it negative 2 to the x, not negative 2 to the x, but negative 2 to the x, it would flip it upside down. So that would look like, it would look like that. The asymptote's still where it was. It just goes down instead of up. Same thing if we had negative 2 to the negative x, it would go down. Technically, this one that I have graphed is still considered growth, because it's, as x is increasing, it's moving away from that x-axis. It's exponential growth in the negative direction. It doesn't have a whole lot of practical value, like in the real world, for applications, so we don't usually think of the negative ones as growth and decay. It's usually just these first two that we look at as growth and decay. But technically speaking, this one's growth, and the other one would be decay. So how could we tell growth or decay just by looking at the equation? It's growth if a is greater than 1. So 2 is greater than 1. It's decay if a is less than 1, but it still has to be bigger than 0. So that would be the 1/2 to the x. Notice in the equation, f of x equals a to the x, it's not a to the negative x. It's a to the x. So we'd need to move that negative into that a value before we would make that decision on whether it's growth or decay. So we can also do transformations. We could make the function f of x equals b times a to the x plus c. The b is going to be a vertical stretch or compression. It's also the y-intercept, as long as c is 0. But that's a vertical stretch or compression. And c is going to be a vertical translation. So it's just going to shift it up and down. It will move the asymptote. C will move the asymptote. The asymptote is actually always y equals c. Doesn't matter if it's growth or decay, or if there's a stretch or not, the asymptote is y equals c. So we have some rules for exponents and exponential functions. The first one, when we are multiplying things, a to the m times a to the n, we add the exponents. This is something we know, but it's also something that gets forgotten. When we divide a to the m over a to the n, we subtract the exponents. If we have a power of a power, a to the m to the n, we multiply the exponents. And then we can also distribute. If we have, say, a b to the m, that can go to both of them. A to the m, b to the m. And then same thing with division. A over b to the m can be a to the m over b to the m. And from here, like, we can combine all sorts of things. So we could have to multiply in the fractions and stuff. You've seen all these rules before. It's just a quick reminder so that we remember that we add the exponents when we multiply. Half-life. Half-life problems get to be way more complicated than they are right now in what we're doing today. Because again, we don't have the use of logarithms quite yet. And I can use that word because I know that you know what a logarithm is, but we haven't gotten there. That's again section 5. So we will get there soon enough, don't worry. But what a half-life is it's the time it takes. Half-life is a time to lose half of its value. So if we have a radioactive isotope that has a half-life of 10 days, that means every 10 days it's going to lose half of what it had. So if it started out with 50 units, or 50 grams, after 10 days there'll be 25 grams. After another 10 days there'll be 12.5 grams. After another 10 days there'll be 6.25 grams. And so it just goes down by a half each time. A way to, sorry, blank there. A way to write an equation for this, if we had to come up with an equation, the amount of something at time t will equal the starting amount times 1/2 to the t. So if we have, say, a half-life of 10 days and we're starting out with 50 grams, the amount of t will equal 50 times 1/2 to the t. Now what's important here is that the t is number of 10-day increments. So when t equals 1, that's 10. When t equals 2, that's 20, because 10 days is our half-life. We could take that into account. If we wanted it to be just each individual day, we could go t divided by 10, but generally speaking, we would just keep it that way. But you just have to recognize that you're looking for that. I mean, we have 10 days. A lot of times, like a half-life might be 3 hours. And so you're looking at like, well, how long would it be for 9 hours? Well, that would be 3 3-hour units. And so you would just put in 3. And so you could find that if you had to figure out when it's going to be 1, how long until 1 gram is remaining, we can't take logarithms quite yet. So what you would do is you would just graph it. Solve by graphing. You would graph the 50 times 1/2 to the t as y1, and y2 you could just graph as 1, and then you figure out where they intersect. It won't be too long, and they intersect. You can use the intersect feature on the graphing calculator. You could use Desmos to graph it if you want, but we're solving that by graphing right at this very moment. And then finally, we have some interest formulas. We have compound interest, and these interest formulas are kind of the same as half-life. You just plug the stuff in. If we have to solve it, it's by graphing. But compound interest, we have the amount you're going to have equals P, that's the principal, that's the starting amount, or the initial amount, times 1 plus r over n. R is the rate. As a decimal, if it's, say, 6.2%, that would be 0.062. We have to remember to convert it to a decimal. N is the number of time increments, the number of times it's compounded in a time increment, usually in a year, because it's going to be an annual percent. So N is going to be the number of times compounded. So if it's compounded quarterly, N would be 4. If it's compounded monthly, N would be 12. If it's compounded daily, N would be 365. And then T would be the number of years, the number of whatever the rate is, like the bigger one. So if it's probably annually. So it'll, in a question like this, it's most likely the number of years. And so that's how you figure out what your amount is. And the reason this happens is, so on the first month, let's say you're getting 12%, so you get like that percent. Well, the second month, you have extra in your account, so that percentage is a little bit bigger. And then the next month, it's a little bit bigger than that. And so that's why this is important. It's not a linear situation. What happens when we increase the number of times we compound stuff, we increase that n value, and it gets bigger and bigger and bigger. This 1 plus r over n to the n becomes e to the r, and we get the natural number e, which is about 2.718281828459045, blah, blah, blah. It's another irrational number, just like pi is, but unlike pi, it's actually interesting. E is my second favorite irrational number. Pi is a distant third at best. So, but we get this E value, and it comes from taking the n of the compound interest formula and making it bigger and bigger and bigger and getting it closer and closer to zero. What happens is we find that that gets to be, it has an asymptote, and that asymptote is E. And so that brings us to when we're compounding stuff continuously. This happens in nature, which is why this is called the natural number. So it happens in nature because when like your radioactive isotope is decaying, it's not thinking like, oh, it's the first of the month, let's take off that little bit. It's doing it all the time. And so the equation here, we get A of t, the amount, equals P. That's still the initial amount. The variable is the same. Then E to the RT. E, this number, to the rate and time. And so for this, you just plug in the values it gives you. If you're looking for how much will be left after a certain amount of time, you plug in, you figure out what A of t is. If you're looking for one of the other values, you would graph it to solve that, because that would include using a logarithm to figure it out. And again, we're not there yet, but we will get there soon. So until then, I will see you in class before then, but until then, keep working problems, keep asking questions, and as always, happy mathing.